also say like, oh, never mind, I get it.
Okay. Okay. Yeah, because this term is going to be added, so the smaller the number, the less harm that it does for the expression. Now, in the third scenario here, the delta H is positive, so that's not favorable. That means the reaction is endothermic, is taking heat in. Reactions don't like that. Delta S, though, is positive, is favorable. Now, that means that this term is positive. That's not good. This does not help a negative delta G to have delta H be positive. This term, though, is also positive. So when I have a positive minus a positive number, we want the answer to be negative. So that means we need a high temperature. That's why that was given. Are you with me on this? It's just thinking mathematically what these numbers have to yield. But man, this comes up. You'll see it. And then if we have an unfavorable delta H and delta S both, I'll just do that. Those are both not great for the reaction. Then it doesn't matter. If I've got a, let's see. If delta H is positive, that doesn't help a negative delta G. And if delta S is negative, I'm taking a positive minus a negative. That's just making it more positive. No matter what the temperature is going to be, it's not going to be spontaneous. Okay? So that's what this slide is all about. Yep, know that one. Do some homework exercises over the weekend. You'll be able to do a lot. And the only thing that we won't be able to do over the weekend is anything about equilibrium. I shouldn't say that. The equilibrium constant. If you see anything about the equilibrium constant, K value, skip that. We'll do it on Monday. Okay? I'd say do all the other problems, though. So you can see what's down here also. You can calculate delta G three different ways. The first way, and the most common, is to use delta H minus T delta S. The second way is to do products minus reactants, which is just like we did delta H. Take the product, delta G minus the negative, or the reactants. This way that you can find delta G is, I guess, aided by the thermodynamic table in the back of the book. The appendix of the book has delta G values for every substance, just like it has enthalpy and entropy. And you can also calculate delta G using Hess's law, just like we did with the enthalpy change too. All right? Each of these boxes has the same number of particles. I just made this slide today, and I was sure to count. Each one has 10 particles in. You don't have to take the time to count. They have, Daniel, don't. They each have 10. Do they all have the same entropy, or is one more than the others? What? Okay, so which one has the most entropy?
It's more, there's more space, so there's more places to be. Yeah.
That's the way I want you to think of that. There's more positional probability in the box on the right. There's more places that the dots can be on the right than there are on the left two. So the one on the right has the most probability. So this is something about gases. When gas pressure is low, the higher the entropy. The lower the pressure, the higher the entropy. The lower the pressure of a gas. That's what I'm... Higher volume / lower pressure, the more entropy that it has. Yeah, the lower the pressure, the higher the entropy. Because the particles are spread out more, there's more positional probability.
Did you just say lower pressure, lower entropy?
No.
Oh, higher.
Yeah, higher entropy. All right. Now, Gibbs came up with another relationship. This one is going to involve a logarithm. You okay with that? Don't get mad.
Yeah.
I have had some people already tell me that they have never done logs before. I wonder if we've recently, I don't know when it happened, but they changed the sequence in the math program. And so if you haven't seen logarithm yet, maybe we need to talk a little bit, because Gibbs came up with this too, and this is where I'll talk about what that degree sign means, because it's going to matter. The free energy of a gas, remember that's what G stands for, is free energy. How much energy is available for doing work is equal to the G with a degree sign plus RT times the natural log of the pressure. Let's talk about that degree sign now and settle this once and for all. The degree sign, I'm going to sound British, and I don't mean to. The way that we express that degree sign is we say naught. This is called G naught. You've heard that before?
No.
Where, Nabil? I didn't hear what you said. The describes things that are what? Yes. Yeah. Where have we? I've heard that context too. I'm not thinking of it.
And everybody in bio kept calling it G naught, and she got mad at them. She was just like, "Where did you get this?" So I guess it's from Chem.
It is from chemistry. Yeah. Yep. And now that you've heard me say it, I'll say it a lot. Yeah. In fact, I try to not let myself say it because you'll be just like for Johnny. Like, what? Oh.
I thought you had laid out some like sick joke out.
Yeah, it's sick joke.
That's so cool. You
All
should
right.
just roll with it.
That's so good.
I didn't even know what I said. So here's what it means. It means standard conditions. And standard conditions are, now this is something that's conditions. 1 mole, 1 atmosphere for gases. Oh, that is so sloppy, my gosh. High entropy on these smart boards. And here's the part that I hate. Oh my gosh. If I could change something about science, I would change this. Standard conditions, when we're talking thermodynamics, is 25 degrees Celsius.
Oh yeah, that's so stupid.
Yeah, it is totally stupid. I'll blame the physics people for this.
For what?
We're at 25.
When we do gas laws, we always say STP, standard temperature and pressure. Standard temperature is what in gas laws? 0 degrees Celsius. We get to doing thermodynamics, literally the next chapter in the book. Now the standard conditions change. And standard temperature when we deal with thermodynamics is 25 degrees Celsius. The gas laws, that should change. That 0 degrees is totally arbitrary. There's no reason. There's nothing special that happens to a gas at 0 degrees. This should be standard for everything. But unfortunately it's not. So you need to know that standard conditions, when we're dealing with thermodynamics, and anytime you see that degree sign, that naught, that means 25 degrees Celsius. Yes?
Why is it so special?
Because this term right here is, when you look up in the appendix of the book, the table values, they're all standard conditions. So it turns out that delta G standard is a constant value. It doesn't change because we're using table values. That number doesn't change. So this number over here, this changes as the pressure of a gas changes and as the temperature of a gas changes. That number right there, though, is what the value would be at standard conditions. So that's a constant value that varies. This term varies. Yes?
What's the value of R?
R, we have to use the 8.31. 8.31 is called the thermodynamic constant. I know it's also called the ideal gas constant, but when we're doing energy like this and we're talking about particle motion, I was about to put kilopascals there, it's not. It's joules per mole Kelvin. Write that down for yourself. When you do anything with R and you're dealing with energy, you got to use 8.31. We've talked about this before. A joule is the same thing as a kilopascal liter. So you know when we did the gas laws, it was 8.31 liters, kilopascals over moles Kelvin. Now that we're dealing with energy, I'm in joules because they're the same thing. Yeah.
Is that not sign the same as the one for delta H?
Mm-hmm. standard conditions.
Which means our lab was technically wrong because. Never mind.
What was wrong?
Because like we were doing the experiment in standard conditions.
The lab that you did the other day?
Yeah.
Did you calculate a delta H with a degree sign? No, you didn't.
Wait, how is it relevant then? Like in terms of.
Well, delta H, if you're just dealing with delta H, is independent of temperature.
Okay.
So even though this gives you a delta G, the degree sign means 25 degrees, delta H will pretty much be the same no matter what temperature, as long as you're in a reasonable range of temperatures.
So like it's not really relevant at all then for delta H.
Let's see, there will be time. No, I guess it's not. It's not. Or delta S. The only time it's really relevant is when you're dealing with delta G. Yep. Okay. What are we doing for time? Not good. So anyway, we have this relationship. The free energy of any gas is equal to the standard free energy plus RT natural log of P. The next thing for us to do is a derivation. And the derivation for thermodynamics it's not bad, but it becomes very messy, but then we clean it up. So we're going to make a mess and then clean it up. It's like the Cat in the Hat movie. So by the end, everything is nice and neat. You okay with that? Unfortunately, I won't be able to get done with it in the less than 10 minutes that we have left. So I'm going to start the derivation and then kind of tease you with it, and then we'll finish on Monday. Okay. Unless you want to just stick around until 2:20 or so. Is that all right?
Yeah,
No.
let's do it. It's a Friday.
Yeah, see? That's good. Fine. Catch your bus. Let's just take a look at this. Fact. This is where we're going to start. I am going to choose a gas phase reaction. All the reactants and products are gases. So we can use this whole G equals G naught plus RT ln of P. Now, I took each of the substances in this, each of the three gases involved in this reaction, and color-coded them so that, the nitrogen is all in green, the hydrogen is all in black, and the NH3, the ammonia, is all in blue.
Right.
I just said black, didn't I? I guess it is time to go home. So, I don't know where I got that from. Anyway, so each gas has its own expression for the free energy that it has. There's a little bit more to it. We know that, I almost hate to do this to you because it does get, just like the movie, The Cat in the Hat. You know the big, gigantic mess that was made? We're going to make a mess like that. We know that delta G is the free energy of the products minus the free energy of the reactants. I'm waiting for you to react. If you're maybe a little forward thinking and think about what I'm about to do.
Well, you're gonna put the stuff in.
Yes.
Oh, I hate that.
That's not good.
Do it all.
The delta G for this this reaction is the free energy of the products minus the free energy of the reactant. That's what I'm showing you there. I have an expression for the free energy of the products and reactants right here, each of them. Oh yes, that's what I'm up to. All right, well, we have, 3 minutes left? Shall we start at least? Hi. Oh, thank you.
Forgot all about it. Sorry about it. Thank you.
Yep.
Wait, so we're gonna have to do natural log on the test without a calculator?
No, I won't expect you to memorize like natural log table. No. I would either ask you a conceptual question about it, or I would say, like, if you wind up with natural log of 2, in the problem I would give you what the natural log of 2 is, so you could do it. Clear?